Hey everyone, welcome back. We're in week 8. So what we're going to talk about today, we're on lab module 3, where we're looking at the TTT diagram and its effect on these steel samples. We're going to go ahead and we're going to prepare our steel samples and get them ready for these annealing treatments. We're also going to perform these heat treatments to create a consistent starting structure. So we're going to do this austenization treatment and make them all the single phase FCC material. And then we're going to cool and anneal in different but controlled ways to manipulate the microstructure. So first, in terms of the sample preparation, I just wanted to clarify the procedure that we're using. It's identical to what we did in our last experiments on the aluminum copper alloys. So we have these chunks of steel. I'm showing them little pictures of them on the left. This was just, again, this 1-inch diameter bar. It was a long bar. I cut it with a bandsaw, and that's a good place to start from, but we need to do a few things. On the right here, I'm showing this sort of from the top down. We're looking at the surface, and then from the side, we can see that it's rectangular. All right. The first thing we need to do is we need to polish this face. So this is pretty rugged, and that's because just how the saw cut it. We want to have a nice smooth surface so that we can do things like measure hardness and also look and etch that surface to look at the microstructure. Now, to help me get that nice polished surface, I'm also going to polish these edges, these corners in this picture on the right here. The idea here is that I want to be able to smoothly wear away material from that surface, and it's very hard if I have a sharp edge at the side. So some material will get dragged along there. I won't be able to get a nice surface. So what I'm really trying to do is take and have a sample that looks a little bit different. It doesn't just look like this rectangular prism shaped chunk. I'm sort of beveling those edges. Here I can see it from the top and also from the side, so that I can then polish the sample and get a nice smooth surface. Just to show you some pictures of these examples during my polishing process. So this is about halfway through. So I've beveled the edges. You can see it there in this image, which is just tilted a little bit with respect to how I'm looking at it. And then this is towards the end, not quite at the end, where we have a much smoother surface. So the light is reflecting off of it, and we're almost at our final structure. Okay. So I'm actually going to show you a few videos of this. I'm trying to do this so I combine it all in one video at the end. So on slide 9, when you click the link, the first video or first part of the video will show you me polishing this. And one thing that comes up compared to our aluminum is that steel has an issue where it likes to rust. Okay, so we have to be very careful when we polish. We're using water to sort of lubricate that process. We want to make sure that we don't leave water on the surface and allow that to corrode. Okay, so getting to our heat treatments, just a reminder, we're going to target 3 microstructures. We're going to heat everything up in this temperature range where it wants to be austenite. We're going to take one sample, cool it down a little bit, but hold it at a relatively high temperature so that we get a pearlite structure. We're going to rapidly quench one down to get martensite. We're going to rapidly quench a second one down to get martensite, but then let it do an intermediate temperature heat treatment to get a tempered martensite, to change the properties further. So we talked about all this in our last set of slides. So this is all pretty straightforward. So these temperatures and these times are things we got. The temperatures from the phase diagram, the times from these TTT diagrams. The one practical thing we need to talk about today is how do we accomplish some of these things. So for example, it doesn't really matter how the ramp rate at which we heat up. That doesn't matter that much. It's going to sit at this really high temperature, so it can just sit there forever. It's fine. But the rate at which we cool down in many of these cases is going to be very important, especially in the case of a martensite. So we want to not allow any of those transformations that the phase diagram predicts to happen. So we really need to rapidly quench it down as fast as possible. We want this curve right here to be as close to vertical as possible. And that's also generally true for after we do our pearlite and tempered martensite annealing treatments. We want to very rapidly quench these down and have a really high slope at the end. Okay. So we need to think about doing that. And the first thing we can play with and change is our quenching medium. So what's the system and material we're going to use to bring that sample down from the high temperature? Generally, people want to use different liquids. So you could put your solid metal in this liquid and cool it down. But you have lots of options. You could really use any sort of liquid. And people do use things like oils and polymer blends to cool things down. But it turns out if you want to very quickly cool down, water is one of the best things you can use. So compared to different oils and things like that, it has a much higher thermal conductivity. Okay, so the basic starting point we're going to take is have a bucket of water, room temperature, and we're going to try to cool down to room temperature using that as our quenching medium. Now, there's some interesting complications that happen. So we're taking a part that's above 900 degrees C, and we're putting it into this much cooler liquid. So that liquid does want to equilibrate and draw out the heat. But the one problem we could run into is the fact that this temperature of this sample is so much higher than the temperature at which liquid water becomes a vapor. Okay, so this is just like we had a phase diagram for these different metals, we can have a phase diagram for water. And you can go and pick out that at 1 atmosphere, so normal environment, the melting or the vaporization temperature for water is 100 degrees C. So this is boiling point. The reason that matters is that this sample with a much higher temperature can result in something called the Leidenfrost effect. So the basic idea is if you have a very, very hot surface and you put a droplet of any liquid, but in this case, it could be water near it, that piece of the liquid that's touching that hot surface can very rapidly heat up, and it can go over that temperature at which the evaporation happens. So what can happen is you end up getting a barrier layer of water vapor that separates that hot solid surface and that liquid droplet, okay? So what really happens is if I just put in my really hot piece of metal, I'll actually get something where I have this insulating layer of the water vapor surrounding my metal, okay? That by itself isn't that bad, but if we remember that we want to rapidly cool this down, that can delay things. So it can keep us from extracting heat in the fastest possible way, okay? This, just to draw a sort of real life analogy, this is why you can take and put your hand into liquid nitrogen. You probably don't want to leave it there for a long time, but the reason that works is that your hand is going to create a vapor layer around it, rather than be touching the actual liquid and getting your hand cooled down to liquid nitrogen temperatures. So there's actually different cooling stages you can think about in water. So you can have this Leidenfrost effect where you have a water vapor bubble around your sample. What you would really like to do is break that up so that you're very rapidly extracting heat from the sample as you're changing liquid water to vapor, but you end up having a bunch of bubbles coming off rather than an insulating layer, okay? Now, eventually, when the temperature of the water gets below the vapor temperature of, or sorry, when the temperature of your sample gets below the temperature at which your water becomes a vapor, then you just have conductive cooling of the sample. So the water, which is a lower temperature, is just extracting heat in the liquid state, okay? So of these, they're really going to worry about on the left side. So what happens at the very high temperatures? And what we want to do is promote this middle type of reaction where we don't have a full layer around our sample, and we're rapidly extracting heat. So we can do this with a few different ways, and we're going to actually follow 2 different techniques. So the first thing we're going to do is we're not going to quench our sample in regular water. We're actually going to do salt water. So the reason for this is that the salt in this solution, so another single phase region of a phase diagram, in this water solution can end up breaking up the formation of these big bubbles. Okay, so it's going to get us closer to that middle point. Now, the other thing we're going to do is we're going to agitate our sample. So rather than me just taking our sample and putting it into the bucket of water, I'm going to take it and move it around to try to sort of mechanically dissipate this Leidenfrost effect as well. All right. So at this point, you can go and you click on the link, again, either on our homepage in Canvas or on the slides that I'll post. What I'm going to do is I'm going to go through how I made the sample, show you the idea of the surface rust being a problem. I will then do the different heat treatments. One thing I want to point out, I talked about it in the videos though, is that we're going to a lot higher temperatures. Before we were only going up to a few hundred degrees. Now we're talking about doing experiments at above 900 degrees C. So what you'll see is that I'm going to have extra safety equipment on. I'm going to take some extra precautions and have it so I'm not even holding the camera. And you'll even see, so our samples, when they're annealing at that high temperature above 900 degrees C, are actually white hot. So they even look different. They're emitting light in that type of temperature range. Okay. Now, at the end of today, we'll have made all of our samples, done the different heat treatments, and then we'll have 3 different microstructures. Then in the next 2 weeks, we can go in and look at their mechanical properties with hardness, and then also do etching of the surface to try to image and look and understand the microstructure that we get. Okay, so go watch the video. That brings us to the end of today, and I will hopefully see you all in some of our working sessions soon. All right, have a good one.